Okay, so far we've talked about 4 different integration techniques. U substitution, integration by parts, trigonometric substitution, and partial fractions. Okay, and those are pretty much the only ones we're going to learn. I mean, that's enough already. But there is the matter that what if you need to use more than one? Okay? And that can definitely happen. And I think that's the main point of this section. It's called Strategy for Integration. Which is a really weird title because, like, I like to think that I know calculus pretty well. I'm getting my PhD in math in a few years, and I think that if you ask me, or any mathematician, what is the strategy for finding an integral, I'd be like, well, it depends on the integral. It depends on what function you're trying to find the integral of, okay? So this is a weird name, and if you look at the section in the textbook, it doesn't really have a lot to say. Like, it says, maybe you could try some things like this, and then that might not work. Tough luck, try again. So I suspect the only real reason for this section is so that they can ask you exercises that involve more than one integration technique. That's my guess. Most of these involve doing some kind of U substitution, and then things go better from there. That's not the only way that you could need more than one technique, but it's one important one. So pretty much for this entire lecture, I'm just going to do some examples. So let's get started. So let's say we're asked to evaluate the following definite integral, e to the x divided by e to the 2x plus 3e to the x plus 2 dx. Now, you look at this for a second, you're like, wait, what? Because there's nothing really that we've talked about that would immediately allow you to handle this in like one step. Partial fractions won't do anything because partial fractions is only for rational functions, which this is definitely not. Trigonometric substitution won't help because this doesn't have an x squared minus a squared minus x squared, or x squared plus a squared in order to make that happen. Integration by parts, I think, would make it even more of a mess. And U substitution, well, let's see where that goes. Okay, so for U substitution, what we're going to do is we're going to say U equals e to the x. If you do that, then du, of course, is going to be e to the x dx. Agreed? All right, so then in that case, what we're looking at here becomes the integral of 1 over u squared plus 3u plus 2 du. All right? Because again, yes, e to the x is u, and that's on top, but also e to the x dx is du. So we could just absorb that into the du. Now then, this one, well, that denominator can be factored. We can factor that into integral of 1 over, I guess, u plus 2, u plus 1. du. And then from there we can do partial fractions on that. All right? So why don't we take a look at how that would go. So that's going to be 1 over u plus 2 times u plus 1. This needs to be equal to a over u plus 2 plus b over u plus 1. You multiply both sides by the denominator, just as always, and you get 1 equals a times u plus 1 plus b times u plus 2. You distribute, and what you get is 1 equals au plus a plus bu plus 2b. And then you collect like terms in powers of u, and you get a plus b times u plus a plus 2b, and this all needs to be equal to just 1, which by the way is 0u plus 1. So, once again, we're saying these two polynomials are equal for every value of u, perhaps some exceptions. So, that means that their corresponding coefficients have to be equal, which means a plus b is going to have to be 0, a plus 2b is going to have to be 1. Alright? So then from there, I suppose the next thing I'd want to do is subtract this second equation minus this first equation. You do that, the a's will cancel. You get 2b minus b, which is just b, and that equals 1. So b equals 1. And of course, if b equals 1 and a plus b equals 0, then a has to be negative 1. Which means that this integral can be rewritten as integral of negative 1 over u plus 2 plus 1 over u plus 1 du. Okay? Now from here, you can just do this as you normally would. You'd split this into two integrals and then handle each through, I suppose, a u substitution. In this case, you might want to call it something other than u, like maybe, I don't know, w or something, just because you're already using u. But in any case, you do that, and eventually what you end up with is negative natural log of the absolute value of u plus 2 plus natural log of the absolute value of u plus 1 plus c. And then that's pretty much our answer. But we need to insert back what u is. So this becomes negative natural log of e to the x plus 2 plus natural log of the absolute value of e to the x plus 1 plus c. Although, now that I'm looking at it, I guess the absolute value signs don't matter anymore because e to the x plus 2 is always positive and e to the x plus 1 is always positive. But whatever, doesn't make a difference. In any case, that is our indefinite integral. Okay? Alright, let's look at another one, shall we? This one is going to be the sine of the square root of 2t dt. So we've got the sine of the square root of 2t dt. And again, you look at this one and you're like, huh? And that's because there's not really anything immediate that would work here, right? What we're going to have to do is another u substitution. And this time we're going to say u equals the square root of 2t. Now, if you do that, then first of all we need to understand this as 2t raised to the 1/2 power. in order to take its derivative. So you take its derivative and you get du will be 1/2 times 2t raised to the negative 1/2 times 2, by the chain rule, dt. The 2's cancel, and then you get 2t to the negative 1/2, which by the way is the same as 1 over the square root of 2t. So this is the same as 1 over the square root of 2t. And let me just emphasize, that is du. And it's like, okay, but where are we going to put this thing? Well, we can move this over to the other side of the equation. We can say that this is the square root of 2t times du equals dt. And if the square root of 2t is the same as u, then this can be understood as u du. And that's the same as dt. That means that what we're looking at here can actually be written as integral of sine u times u du. Which of course is the same thing as the integral of u sine u du. Okay? And then this is a quintessential integration by parts problem. So I guess I don't really want to call the two things u and v, so I'll call them w and v. I'll say w is equal to u, and dv is equal to sine u du. In that case, dw is du, and v is going to be negative cosine u. Now then, in that case, this becomes uv, so that's going to be, or actually wv, so in this case that's going to be negative u cosine u minus the integral of v dw, which in this case is just going to be negative cosine u du. And now from here, of course, the antiderivative of cosine u is just sine u, which means that what we're looking at here becomes negative u cosine u plus sine u plus c. From here, once again, we just need to say u is the same as square root of 2t, and then our answer just becomes sine of the square root of 2t minus the square root of 2t cosine of the square root of 2t plus c. And that is our indefinite integral. All right. Okay. So here's another one. This one is similar, but not quite the same. This one gives us the cosine of 1 over x divided by x cubed. Well, let's see here. If we do a u substitution on this, if we say u equals 1 over x, well, of course, 1 over x is the same as x to the negative 1, and then you can do the power rule on that and get the derivative is negative x to the negative 2. So then du is negative x to the negative 2 dx, which, by the way, is the same as negative 1 over x squared dx. Alright, that's great and all, but that's an x cubed, not an x squared. So how will you take care of this? Well, one way to do it is to say, all right, well, yeah, we've got negative du equals 1 over x squared dx. And that handles two factors of u on the bottom. No, not u. Two factors of x on the bottom. The other factor of x can be understood as u, because u is 1 over x. So this same thing can be written as integral of u cosine u du. Actually, there's a negative sign. There we go. Negative u cosine u du. All right. Now from here, once again, this also is a quintessential integration by parts problem. So you do the regular thing. Again, I don't want to use u for integration by parts, so I'll call it w. So w is going to be u. dv is going to be cosine u du. Then dw is going to be du, and v is going to be sine u. This now becomes negative. Let's see, wv is going to be u sine u, and then plus the integral of vdw is going to be sine u du. And if you're wondering why this is plus and not minus, it's because I distributed this minus sign. Okay. So now antiderivative of sine u is just negative cosine u, which means that this is just going to become negative u sine u minus cosine u plus c. And we need to insert back what u is, so this is just going to be negative sine of 1 over x times 1 over x minus cosine of 1 over x plus c. And that is our indefinite integral. All right. Now, let's try one more. This one is a little bit of a twist. So this one is going to be arctangent x over x squared. Okay. So we have arctangent x over x squared dx. Now this one is a bit different because I don't see a u substitution that would be helpful here. Do you? I mean, if you make u equal to arctangent x, then du would become 1 over 1 plus x squared dx. And, you know, that'd be great if this were like 1 plus x squared in the denominator, but it's just x squared. So then how do you handle this one? Probably the easiest way to do it is to begin with integration by parts. Right? So if you're going to do integration by parts, then you're going to have to select a u whose derivative you know, and you're going to have to select a dv whose antiderivative you know. Now, 1 over x squared, we know both its derivative and its antiderivative. As for arctangent x, though, I don't know its antiderivative. I only know its derivative. So, probably it'd be easiest to say u equals arctangent x. So if u equals arctangent x, then dv is going to be forced to be 1 over x squared dx. Now from here, du is going to be 1 over 1 plus x squared dx, and v is going to be, what is this, negative 1 over x? Yeah, that's just the power rule because this is actually x to the negative 2. Okay. Alright, so now integration by parts says we're going to have uv minus the integral of v du, so that's going to be negative arctangent x times 1 over x minus the integral of v du, so that's going to be negative 1 over x times 1 plus x squared. Alright. So now, alright, I guess that's doable, right? It's certainly better than this one, right? Okay. So, I think there's more than one way to handle this one. I think you can definitely do partial fraction decomposition, which I suspect that's what I did in my notes. Yes, that is exactly what I did in my notes. But I think you can also handle this by doing a trigonometric substitution. You could say x equals tangent theta, and then go from there. But we'll do partial fractions here. So what we want to do is we want to decompose 1 over x times 1 plus x squared into two fractions. The first one is going to be a over x, and the second one is going to be bx plus c divided by 1 plus x squared. Okay, and again, just like in the last lecture about partial fractions, 1 plus x squared is an irreducible quadratic, which means we cannot factor it, and so therefore it's just going to have to be in one of these denominators. And then if you have an irreducible quadratic in the denominator, you have to have a general linear polynomial in the numerator, which means bx plus c. Okay. Now then, you go ahead and multiply through by x times 1 plus x squared, and what you get is 1 equals a times 1 plus x squared plus bx plus c times x. From here, we can say, all right, well, that means 1 is going to be a plus ax squared plus bx squared plus cx. And then from here we can collect like terms and powers of x. So what we'll get here is 1 equals, let's see here, we have a plus b times x squared, and then plus cx plus a. There we go. So now once again, these two polynomials are equal for all values of x. And so therefore their corresponding coefficients are equal, which means a plus b has to be 0. So a plus b equals 0. And c is going to have to be 0. And a is going to have to be 1. Alright? Now from here, c is 0, a is 1, fine, and then b has to be negative 1. Alright? So then this means that our integral now becomes, let's see, we still have negative arctangent of x divided by x outside, but then this part becomes integral of, let's see, here is going to be 1 over x plus negative 1x divided by 1 plus x squared, so that's minus x over 1 plus x squared dx. This now we can just split apart into two different integrals. So now this becomes, let's just draw a little partition here so we don't get confused. So this becomes negative arctangent x divided by x plus the integral of 1 over x dx minus the integral of x over 1 plus x squared dx. Right? As for this one, we just say u equals 1 plus x squared and then du becomes 2x dx. And then this one is just going to be natural log of the absolute value of x, right? So what we get here is negative arctangent x divided by x plus natural log of the absolute value of x, and then minus 1/2 integral of 1 over u du. Now this becomes natural log of the absolute value of x minus arctangent x divided by x minus 1/2 natural log of the absolute value of u plus c. But u is 1 plus x squared, which means this is just natural log of 1 plus x squared plus c. Right? And so this is our indefinite integral. Okay? So, naturally, all of the examples I did today, I saw them before because I had to prepare the lecture, obviously. Now, when you see these integrals for the first time, you may find yourself a little bit stumped, okay? That can happen. You may have to take a minute to be like, well, let's see, if I try this, then maybe that'll work, and if I try this, maybe that won't work, so let's try this and see what happens. And then maybe you'll try something and get nowhere, and then say, all right, well, we'll just have to try something else. It happens. That's how math is done a lot of the time. You just have to do what you can, do your best, and then if it doesn't work out, try something else. Okay? But the point that I'm trying to drive home here is, despite the name of this section, there is no real strategy here. You just kind of have to do something, and then if it doesn't work, try something else. Okay? There's no really easy way to predict what's going to happen, because as we've seen from my screw up on quiz 2, you can just change one tiny thing about a math problem and then it becomes completely different. Okay? And yeah, that's how antiderivatives go. So, homework is up. It's pretty challenging, naturally. So of course, let me know if you need any help on it. All right? Get some practice with that.